Imagine working your entire life to decode the deepest secrets of the cosmos, only to have your data scrambled because someone nearby got hungry. In 2007, astronomers analyzing archival data from the massive Parkes radio telescope in Australia found something extraordinary: the Lorimer burst. This was the first ever recorded fast radio burst, or FRB. It was a millisecond-long pulse of radio waves, carrying as much energy as our sun produces in an entire month, and it had traveled across billions of light-years to reach Earth. This single pulse offered researchers a way to map the mass of the universe and study its expansion. Astrophysics was buzzing with the possibilities, until a second, highly suspicious set of signals appeared in 2010. Researchers called these new pulses peritons, after a mythological winged elk that casts the shadow of a human, appearing as something it is not. The name fit. Peritons looked exactly like fast radio bursts, but their data signature strongly suggested they were originating right here on Earth. This triggered a crisis in the field. If peritons were just local interference masquerading as cosmic events, the original Lorimer burst might be a fake. Lacking a clear explanation, active follow-up work on FRBs largely paused, and many researchers abandoned the search. To rescue the science, a PhD student named Emily Petroff led an international team to catch a periton in the act. In January 2015, they installed a real-time radio frequency interference monitor at the Parkes site to continuously scan for local noise. To understand why peritons were such convincing fakes, researchers looked at cold plasma dispersion. As a radio pulse travels through interstellar space, plasma acts like a drag force on lower frequencies. High frequencies race ahead, creating a distinct sweeping curve over time. This chart displays a periton signal against the background noise of the telescope. You can see the bright, downward sweeping dispersive curve. It is a perfect quadratic sweep, completely identical to the math of cold plasma dispersion. This is why the problem was so severe. If a terrestrial glitch could generate the exact mathematical signature of a billion-year cosmic journey, astronomers had no reliable way to prove any deep space radio discovery was actually real. Petroff's team started finding anomalies. A distant FRB hits a telescope from a single concentrated point in the sky, lighting up just one or two receiver points. But the peritons were hitting all 13 of the telescope's receivers at exactly the same time. This wide-field detection proved the source was likely within the observatory campus itself. Then, the new interference monitor caught something crucial. This spectrogram shows radio frequencies over time. The bright interference marks appearing right around the 2.4 GHz range occurred at the exact millisecond a 1.4 GHz periton was detected. The 2.4 GHz frequency is heavily regulated. It's the designated band for industrial and scientific tools, domestic wireless networks, common Bluetooth devices, and kitchen microwave ovens. Looking at historical data, a behavioral pattern emerged. This bar chart tracks the time of day peritons were recorded. The massive central spike sits squarely between 12 and 2 p.m. on weekdays. They were happening at lunchtime. The mechanical culprit was a microwave oven's magnetron, the high-power vacuum tube that generates the radiation to heat food. When operating, it pushes out a 2.45 GHz wave. If you yank the door open prematurely while the timer is still ticking down, the magnetron enters a shutdown phase, instantly leaking a sweeping burst of energy. An impatient scientist stopping their lunch a few seconds early was inadvertently broadcasting a millisecond radio sweep that perfectly mimicked the physics of interstellar space. On March 17, 2015, the team put this deduction to the test. They placed a ceramic mug of water into the vintage National brand microwave. They pointed the massive telescope dish directly at the building, started the timer, and pulled the door open early. This graph displays the result of that exact test. The bright head and textured tail sweep you see here is an artificially generated periton, appearing right on command. With the fake definitively identified, researchers could confidently filter their archival data. They looked back at the original 2007 Lorimer burst. It was a clean, single beam effect, and it lacked any of the 2.4 GHz microwave interference traits. The Lorimer burst was genuine, the discovery was valid, and the field of transient radio astronomy was instantly rehabilitated. Today, facilities around the globe discover multiple fast radio bursts every single day. Astronomers are now tracing these authentic signals back to magnetars, rapidly spinning, highly magnetized dead stars, violently releasing energy in deep space. Every new burst we record brings us closer to mapping the web of matter between galaxies. What do you think is the next great space mystery we'll untangle? Let us know in the comments and subscribe for more deep dives into the unknown. It took 5 years to untangle the data, but the quest to map the furthest reaches of the cosmos was ultimately saved by understanding the precise mechanics of a heated lunch.